Studies Section 4. Optimization Problems. Introduction. The common criterion of choice among alternatives in economics is for maximizing or minimizing problems. Conventionally, the primary objective of a firm is to maximize profit, while the basic objective of consumer is to maximize utility from consuming one or some combinations of commodity bundles. Also, firms are out to minimize cost of producing a certain level of output, while consumers are willing to minimize expenditure on attaining a given level of utility. The question that follows is, at what level of output are profits maximized, or what is the minimum cost that can produce a specific level of output? In the case of consumers, we are faced with the questions of what is the level of consumption, combination for which maximum utility is realized, or what is the minimum expenditure that will achieve a certain level of utility. When we are trying to find answers to these questions, we are actually optimizing, seeking the best alternative. Broadly speaking, there are two categories of optimization: unconstrained optimization and constrained optimization. In this study section, we shall be dealing with both constrained and unconstrained optimization and the methods of finding the maximum or minimum level of the choice variable. Objectives. At the end of this study section, you should be able to 1. Identify conditions for which a function is minimized or maximized. 2. Use the various methods for finding minimum or maximum value of a function. And 3. Solve some economic problems that has to do with optimization. Pretext. 1. State the condition for which a function is maximized or minimized. Given the function y equal to x cubed plus x squared minus 3x, what is the level of x for which the function is maximized or minimized? 2. What do you understand by constrained optimization? Maximize the following production function q is equal to 3kl subject to 2pk plus 5pl is equal to 100. Content. In optimizing any function, we need to identify the objective function and the choice variables. The objective function is the function that we want to maximize or minimize. The choice variables are the variables to be manipulated in order to get the expected result, either maximization or minimization. Consider the following profit function. Pi into bracket q is equal to r into bracket q minus c into bracket q, equation 4.1, where q is the output level, r and c are total revenue and total cost, respectively. Assuming we want to maximize equation 4.1, the profit function, in this case, pi is the dependent variable which represents the object to maximize, while r into bracket q and c into bracket q are independent variables or choice variables. Generally, given the function y equal to f of x, we may attempt to develop a procedure for finding the level of x that will maximize or minimize the value of y. Unconstrained optimization. Maximum and minimum value. We need to differentiate between absolute or global and relative or local maximum and minimum value. Consider the three graphs below in panel A. The value of x will result in the same value of y. Hence, the height of each point A, B, and C can be considered as maximum and minimum or neither. This occurs when the function is constant. In panel B, we see that the function keeps on increasing. Point D is called absolute minimum because there is no other point lower than that. However, since the function keeps on increasing, we cannot identify the maximum point. In panel C, we cannot consider point E as the global minimum. Also, we cannot consider point F as the global maximum because the function may either decrease or increase further. Thus, points like E and G are called relative local minimum, while point like F is called relative local maximum. In most economic problems, we usually deal with relative extremum of this type. Relative extremum is a point at which a function is at a relative maximum or minimum. It must be added that a point in the domain of a function where the derivative equals 0 or is undefined is called a critical point or value. We use the concept of derivative to determine whether a function is at its relative minimum or maximum. For convenience, we shall refer to the derivative of function as first-order derivative. For an extremum to exist, the necessary condition is that the first derivative must be 0. The value of the function when its first derivative is set to 0 is called the critical point. A relative extremum must also be a stationary value, but a stationary value may be associated with either a relative extremum or inflection point. Stationary value is the value that a function assumes at its critical value. An inflection point occurs at the point where no particular direction of a slope is determined. Unconstrained optimization with univariate function. To find the relative maximum or minimum of a univariate function, f of x, take these steps. A. Take the first order derivative and set it equal to 0, first order condition. B. Obtain the critical point by evaluating the value of f prime of x is equal to 0. C. You may find the stationary values of the function. This is established by plugging the values of the critical point in f of x. D. Take the second derivative, f prime prime of x, second order condition, and E. Evaluate it at the critical points and check the signs. If at a particular critical point x, f prime prime of x is less than 0, the function is at a relative maximum concave. If f prime prime of x is greater than 0, the function is at a relative minimum convex. The first order derivative gives the necessary condition, while the second order derivative gives the sufficient condition. Example 1. Optimize f of x is equal to 2x cubed minus 30x squared plus 126x plus 59. Take the first order condition to establish the necessary condition. F prime of x is equal to 6x squared minus 60x plus 126 is equal to 0. Evaluate this function to get the critical point. The function has turned to quadratic equation, and thus to evaluate, we shall use quadratic formula. This can be done by factorization or by adopting the general formula for quadratic equation. In this example, we use the formula 6 into bracket x minus 3 bracket closed into bracket x minus 7 bracket closed is equal to 0. X is equal to 3, x is equal to 7, critical point. Take the second order derivative, evaluate it at the critical point, and determine the status of the function. F prime prime of x is equal to 12x minus 60. F prime prime into bracket 3 is equal to 12 into bracket 3 minus 60 is equal to 36 minus 60 is equal to minus 24 less than 0. relative maximum. F prime prime into bracket 7 is equal to 12 into bracket 7 minus 60 is equal to 84 minus 60 is equal to 14 greater than 0 relative minimum. To obtain the stationary point, plug x is equal to 3 and x is equal to 7 in the f of x function. We conclude, therefore, that the function f of x is at maximum when x is equal to 3 and it is at minimum when x is equal to 7. Example 2. Find the relative extremum of the function y is equal to f of x is equal to s cubed minus 12x squared plus 36x plus 8. F prime of x is equal to 3s squared minus 24x plus 36 is equal to 0. Divide throughout by 3 is equal to s squared minus 8x plus 12 is equal to 0. Then factorize. You have x squared minus 2x minus 6x plus 12 is equal to 0. X into bracket x minus 2 minus 6 into bracket x minus 2 is equal to 0. X minus 6 into bracket x minus 2 into bracket is equal to 0. Hence, x is equal to 6, x is equal to 2. Critical point. F prime prime of x is equal to 6x minus 24. F prime prime into bracket 6 is equal to 6 into bracket 6 minus 24 is equal to 36 minus 24 minus 12 greater than 0 relative minimum. F prime prime into bracket 2 is equal to 6 into bracket 2 minus 24 is equal to 12 minus 24 is equal to minus 12 less than 0 relative maximum. We thus conclude that the function f of x is at relative minimum when x is equal to 6 and at maximum when x is equal to 2. Application to economics. 1. Find the optimal value for average cost when AC is equal to f of q is equal to q squared minus 5q plus 8, where AC is average cost and q is level of output. Take the first order derivative FOD is equal to the necessary condition f prime of q is equal to 2q minus 5 is equal to 0. Q is equal to 5 over 2 is equal to 2.5. Critical point. The second order derivative 2OD is equal to the sufficient condition f prime prime of x is equal to 2 greater than 0 relative minimum. Hence, the minimum average cost MAC is attained when output is 2.5 units. 2. Maximize the profits pie for a firm given total revenue and total cost functions. R is equal to 4000Q minus 33Q squared. C is equal to 2Q raised to power 3 minus 3Q squared plus 400Q plus 5000, where R and C are total revenue and total costs, respectively, and Q is level of output. Determine the profit function first using the formula pi is equal to R into bracket Q minus C into bracket Q. Pi is equal to 4000Q minus 33Q squared minus parenthesis open 2Q raised to power 3 minus 3Q squared plus 400Q plus 5000 parenthesis closed is equal to minus 2Q raised to power 3 minus 30Q squared plus 3600Q minus 5000. Now take FOD of the profit function. Pi is equal to minus 6q squared minus 60q plus 3600 is equal to 0 is equal to minus q squared minus 10q plus 600 is equal to 0. Applying general formula for quadratic equation, we find out that the critical points are q is equal to minus 30, q is equal to 20. We need to determine which of the q's actually maximizes profit. This is done by taking the 2OD. Pi prime prime is equal to minus 12q minus 60. Pi prime prime into bracket minus 30 is equal to minus 12 into bracket minus 30 minus 60 is equal to 360 minus 60 is equal to 300 greater than 0, relative minimum. Pi prime prime into bracket 20 is equal to minus 12 into bracket 20 minus 60 is equal to minus 240 minus 60 is equal to minus 300 less than 0, relative maximum. Hence, the maximum profit is attained when output level reaches 20 units. What is the profit at this level of output? To find this, substitute 20 for q in the profit function. Pi into bracket 20 is equal to minus 2 into bracket 20 raised to power 3 minus 30 into bracket 20 raised to power 2 plus 3600 into bracket 20 minus 500 is equal to 39,000. Meaning that the optimal profit is 39,000 and the level of output that generates this profit is 20 units. 3. A firm has the following total cost and demand functions. C is equal to 1/3 q raised to power 3 minus 7q squared plus 111q plus 50. QD is equal to 100 minus P, where C and QD are total cost and quantity demanded, and P is unit price of output Q. Formulate the total profit function. Determine the profit maximizing level of output Q asterisk. What is the maximum profit at this level of output? Formulate the profit function as follows. Pi is equal to R into bracket Q minus C into bracket Q. R into bracket Q is equal to PQ. Thus, pi is equal to PQ minus C into bracket Q. From the problem given, P is equal to 100 minus Q. Why? Thus, R into bracket Q is equal to 100 minus Q into bracket closed Q is equal to 100Q minus Q squared. Pi is equal to 100Q minus Q squared minus bracket open 1/3 Q raised to power 3 minus 7Q squared plus 111Q plus 50 bracket closed is equal to 100Q minus Q squared minus 1/3 Q raised to power 3 plus 7Q squared minus 111Q minus 50 is equal to minus 1/3 Q raised to power 3 minus Q squared plus 7Q squared plus 100Q minus 111Q minus 50. Pi is equal to minus 1/3 Q raised to power 3 plus 6Q squared minus 11Q minus 50 is equal to profit function. To find the profit maximizing level of output, take the FOD of the profit function and find the critical point. Pi is equal to minus Q squared plus 12Q minus 11 is equal to 0. Simplifying using general formula for quadratic equation, we have Q is equal to 1, Q is equal to 11 critical points. Take the 2OD to establish which of the two values of Q satisfies sufficient condition for maximum. pi prime prime is equal to minus 2 cube plus 12. Pi prime prime into bracket 1 is equal to minus 2 into bracket 1 plus 12 is equal to minus 3 plus 12 is equal to 9 greater than 0, relative minimum. Pi prime prime into bracket 11 is equal to minus 2 into bracket 11 plus 12 is equal to minus 22 plus 12 is equal to minus 10 less than 0, relative maximum. Thus, the profit maximizing level of output is 11 units. To find the maximum profit at this level of output, insert 11 into the profit function. Pi is equal to minus 1 over 3 into bracket 11 raised to power 3 plus 6 into bracket 11 squared minus 11 into bracket 11 minus 50 is equal to minus 1 over 3 into bracket 1331 plus 726 minus 121 minus 50 is equal to minus 443 into bracket 1 over 6 plus 726 minus 121 minus 50. Pi is equal to 111.3 or 111 odd number 1 over 3. Unconstrained optimization with multivariate functions. We may encounter a situation whereby the objective variable is a function of more than one decision variables. In this case, we need to modify our rules in order to capture this scenario. For a multivariate function, such as z is equal to x, y into bracket, to be a relative minimum or maximum, 3 conditions must be satisfied, and these are: A. The first order partial derivative FOPD must equal to 0 simultaneously. B. The second order partial derivative 2OPD, when evaluated at the critical point, must both be negative for a relative maximum and positive for a relative minimum. C. The product of the 2OPD evaluated at the critical point must exceed the square of the second order cross partial derivative 2OCPD, also evaluated at the critical point. The importance of the third condition is to preclude the inflection or saddle point. In summary, for a two-variable function, say z is equal to x, y in bracket, f of x, f of y is equal to 0, necessary condition. F of xx, f of yy is less than 0, condition for maximum. F of xx, f of yy greater than 0, condition for minimum. F of xx, f of yy greater than f of x into bracket squared, sufficient condition for relative maximum or minimum. Examples: optimize the following unconstrained function: z is equal to 2y cubed minus x cubed plus 147x minus 54y plus 12. Take the FOPD and set them at 0. Zx is equal to minus 3x squared plus 147 is equal to 0. Hence, 3x squared is equal to 147. X squared is equal to 147 over 3 is equal to 49. X is equal to plus or minus square root of 49. X is equal to plus or minus 7. For zy, zy is equal to 6y squared minus 54 is equal to 0. 6y squared is equal to 54. Y squared is equal to 57 over 6. Y squared is equal to 9. Y squared is equal to plus or minus square root of 9. Y is equal to plus or minus 3. We now have 4 critical point viz. X 7 minus 7, 7 minus 7. Y 3, 3 minus 3 minus 3. Next, take the two OPD, evaluate them at each critical point and check the relative extremum. ZXX is equal to minus 6x. ZXY is equal to 0. ZYY is equal to 12y. ZYX is equal to 0. ZXX into bracket 7, 3 is equal to minus 6 into bracket 7 is equal to minus 42 less than 0. ZXX into bracket minus 7 comma 3 is equal to minus 6 into bracket minus 7 is equal to 42 greater than 0. ZXX into bracket 7 comma minus 3 is equal to minus 6 into bracket 7 is equal to minus 42 less than 0. ZXX into bracket minus 7 minus 3 is equal to minus 6 into bracket minus 7 is equal to 42 greater than 0. ZYY into bracket 7, 3 is equal to 12 into bracket 3 is equal to 36 greater than 0. ZYY into bracket minus 7, 3 is equal to 12 into bracket 3 is equal to 36 greater than 0. ZYY into bracket 7 minus 3 is equal to 12 into bracket minus 3 is equal to minus 36 less than 0. ZYY into bracket minus 7 minus 3 is equal to 12 into bracket minus 3 is equal to minus 36 less than 0. Now take the third and sufficient condition and verify which of the two OPDs meet the condition. Minus 42.36 less than 0 bracket squared violates the rule, thus we strike this out. 42.36 greater than 0 in bracket squared satisfies third order condition. The critical points are a candidate. Minus 42.36 greater than 0 in bracket squared satisfies third order condition. The critical points are a candidate. 42.36 less than 0 in bracket squared violates the rule, thus we strike this out. Two sets of the four critical points satisfy the sufficient condition. The first one is when x is equal to minus 7 and y is equal to 3. The second is when x is equal to 7 and y is equal to minus 7. This implies that the function is at minimum when x is equal to minus 7 and y is equal to 3. The function is at maximum when x is equal to 7 and y is equal to minus 3. Constrained optimization. Up to this point, we assume that the objective function being optimized has no constraints. In real life, particularly in economic analysis, there are several constraints that face a given objective. For instance, the optimal level of utility derived from a particular set of commodity depends on the income level of the consumer and the prices of the goods, among others. Thus, income and prices of goods serve as constraints to consumer satisfaction. We therefore need to recognize these limiting factors and incorporate them in our optimization problem. Consider a consumer with a simple utility function of the form U is equal to x1 x2 plus 2x1, equation 4.1. It is straightforward to verify that without any constraint, the consumer will tend to continue consuming the goods until he is tired. Assuming that the utility function is subject to the purchasing power of the consumer, the budget constraint. Assuming further that the consumer intends to spend 60 naira on the two goods and the current prices of the goods are 4 naira and 2 naira respectively. The budget constraint is written as follows: 4x1 plus 2x2 is equal to 60, equation 4.3. What will be the commodity bundles that maximizes consumers' utility? We can solve this using three methods: substitution method, Lagrangian multiplier method, and Bode-Einstein method. The use of substitution method. Solve for x1 in terms of x2 in equation 4.2 and substitute this in equation 4.1. x1 is equal to 60 minus 2x2 over 4, equation 4.4. Hence, u is equal to x2 into bracket 60 minus 2x2 over 4 plus 2 into bracket 60 minus 2x2 over 4. Simplifying, we have 56x2 minus 2x2 squared plus 120, equation 4.5. Now, take the FOD and set it equal to 0 to obtain the critical point. Ux2 is equal to 56 minus 4x2 is equal to 0, equation 4.6. The critical point gives x2 is equal to 56 over 4 is equal to 14. Plug this value in 4.3 to obtain the critical value of x1. x1 is equal to 60 minus 2 into bracket 4 over 4 is equal to 32 over 4 is equal to 8. The stationary value can be found by inserting the critical point into the objective function, equation 4.1. Ux is equal to 8 into bracket 14 plus 2 into bracket 8 is equal to 112 plus 16 is equal to 128. To determine the relative extremum status, take the 2OD. Ux2 x2 is equal to minus 4 less than 0 relative maximum. Thus, given the budget constraint, the maximum level of utility is attained when the consumer buys and consumes 80 units of x1 and 14 units of x2. The maximum utility attained from the consumption of this good is 128 utils. Example 2. Let the production function of a firm be Q is equal to 4k squared plus 3kl plus 6l squared. Let the per unit cost of L and K be 1 naira each, and the amount available for the purchase of this factor inputs is 56 naira. Determine the optimal level of output. Set up the objective and cost constraint problems. Maximum 4k squared plus 3kl plus 6l squared, equation 4.7. xt k plus l is equal to 56, equation 4.8. By substitution method, using equation 4.8, k is equal to 56 minus l. Substituting equation 4.9 in 4.7, we have q is equal to 4 into bracket 56 minus l squared plus 3 into bracket 56 minus l plus 6l squared is equal to 112664 minus 448l plus 4l squared plus 156l plus 6l squared. 12664 minus 282l plus 10l squared, equation 4.10. Now take the FOD of equation 4.9. QL is equal to minus 282 plus 20L is equal to 0, equation 4.11. L is equal to 282 over 20. L is equal to 14.1. equation 4.12. Substitute equation 4.12 for L in equation 4.9. K is equal to 56 minus 14.1 is equal to 41.9, which is approximately 42. Equation 4.13. To find the stationarity point, plug equations 4.12 and 4.13 in 4.7. Q is equal to 4 into bracket 42 squared plus 3 into bracket 42 into bracket 14 plus 14 squared is equal to 7056 plus 1764 plus 196. Q is equal to 9016. Thus, given the cost constraint faced by the firm, the level of input combinations that maximizes output are 42 units of capital and 14 units of labor, and the optimal level that can be produced is 9016 units. The use of Lagrangian method. We can handle the constraint optimization with the use of Lagrangian multiplier. Example: use Lagrangian multipliers to optimize the following functions subject to the given constraint. Z is equal to 4x squared minus 2xy plus 6y squared subject to the constraint x plus y is equal to 72. Steps to take. Set up the constraint equal to 0, multiply it by lambda, and add it to the objective function. Take the FODs of the function and set it to 0. Obtain the critical point. Put the values of the critical point into the primitive function to obtain the stationary point. Test for the necessary condition using the same process discussed earlier. Taking the first step, we have z is equal to 4x squared minus 2xy plus 6y squared plus lambda into bracket 72 minus x minus y, equation 4.14. Second step, zx is equal to 8x minus 2y minus lambda is equal to 0, equation 4.15. zy is equal to minus 2x plus 12y minus lambda is equal to 0, equation 4.16. Z lambda is equal to 72 minus x minus y is equal to 0, equation 4.17. Third step, from equations 4.15 and 4.16, 8x minus 2y is equal to minus 2x plus 12y. Hence, 10x is equal to 14y. Y is equal to 10 over 14 is equal to 0.7x. Equation 4.18. Substitute equation 4.18 into 4.17. 72 is equal to x plus 0.7x. 72 is equal to 1.7x. X teres is equal to 42.5, equation 4.19. Substitute 4.19 into equation 4.18 to obtain the value of y. Y teres is equal to 1.7 into bracket 42.5 is equal to 29.75. Substitute the values of x teres and y teres into equation 4.16 to obtain the stationary point. Z is equal to 9936. Utility maximization with constraint. Consider the utility of a consumer described as follows. U is equal to U into bracket xy, bracket open, ux, comma, uy greater than 0, bracket closed, subject to px x plus py y is equal to I. Maximize the utility subject to income constraint. Set up the Lagrangian function. L is equal to U into bracket xy plus lambda bracket opened I minus pxx minus pyy, bracket closed, equation 4.20. The FOD of 4.18 yield the following: Lx is equal to ux minus lambda px is equal to 0, equation 4.21. Ly is equal to uy minus lambda py is equal to 0, equation 4.22. L lambda is equal to I minus pxx minus pyy is equal to 0, equation 4.23. Equations 4.19 and 4.20 are equivalent to ux over uy is equal to px over py is equal to lambda, equation 4.24. Rearranging, we have ux over px is equal to uy over py is equal to lambda, equation 4.25. Equation 4.23 says that in order to maximize utility, consumers must allocate their budgets so as to equalize the ratio of marginal utility to own price for every commodity. The term lambda is the marginal utility of money. Profit maximization and cost constraint. Let the profit function of a firm be of the form pi is equal to pi into bracket k L subject to WL plus RK is equal to Y, where pi is the profit, K and L are quantities of capital and labor, while W and R are wages rental rates. The maximum profit is attained as follows: Z is equal to pi into bracket KL plus lambda into bracket Y minus WL minus RK, equation 4.26. The FOD of the function gives ZK is equal to pi k minus lambda R is equal to 0, equation 4.27. ZL is equal to lambda L minus lambda W is equal to 0, equation 4.28. Z lambda is equal to Y minus WL minus RK is equal to 0, equation 4.29. From equations 4.27 and 4.28, we generate equation 4.30 below. Pi k over pi L is equal to R over W is equal to lambda, equation 4.30. The interpretation of equation 4.28 is similar to utility maximization problem discussed earlier. Using border ASEAN to handle optimization problems. Elementary understanding of bordered ASEAN in optimization, most especially in the case of multivariate equations. There are three conditions to be met. Given y is equal to x1, x2 in bracket, first condition, f of x1 is equal to 0, of f of x2 is equal to 0. Second condition, f x1 x1 is equal to f x2 x2 greater than 0, relative minimum. F x1 x1 f x2 x2 less than 0, relative maximum. Third condition, f x1 x1 dot f x2 x2 greater than f x1 x2 in bracket squared. One simple way for establishing the second condition, particularly when we are dealing with more than two variables, is the use of bordered ASEAN. A Hessian is a determinant composed of all the second order derivatives, while the second order direct partials are on the principal diagonal. The second order cross partials are on the off the principal diagonal. To make things easy, let us for a moment consider a bivariate function of the form y is equal to f of x1 x2. The second order derivative and the second order cross partial derivative can be arranged in matrix format as follows. Bracket opened, fx1 x1, fx1 x2, fx2 x1 fx2 x2 bracket closed. Hence, modulo capital H is equal to bracket open fx1 x1 fx1 x2 fx2 x1 fx2 x2 bracket closed. We need to solve for the determinant of the principal minors. In the matrix above, there are two principal minors. The first one is got by deleting the last row and the last column. This gives the first element on the principal diagonal, that is, modulo h1 is equal to fx1 x1. The second principal minor is given by modulo h2 is equal to bracket open fx1 x1 fx1 x2 fx2 x1 fx2 x2 bracket closed is equal to fx1 x1 dot fx2 x2 minus fx1 x2 dot fx2 x1 is equal to fx1 x1 dot fx2 x2 minus fx1 x2 in bracket squared. Rules for maximum and minimum for bivariate function. If the value of modulo h1 and modulo h2 are positive, then the Hessian modulo h is called positive definite. A positive definite Hessian satisfies the second order condition for relative minimum. If the value of modulo h1 is negative, while the value of modulo h2 is positive, then the Hessian modulo h is called negative definite. A negative definite Hessian satisfies the second order condition for relative maximum. Let us now extend our analysis to three variables. Let y is equal to function of x1, x2, x3. The second order for the variables is fx1, x1 is equal to y11, fx2, x2 is equal to y22, fx3, x3 is equal to y33, fx1, x2 is equal to y21, fx1, x3 is equal to y31, fx2, x3 is equal to y32, fx2, x1 is equal to y12, fx3, x1 is equal to y13, fx3, x2 is equal to y13. Modulo h is equal to bracket open y11, y12, y13, y21, y22, y23, y31, y32, y33 bracket closed. Question 4.31. Next, we need to find the determinant of the principal minors. Since this is a 3 by 3 matrix, we shall have three principal minors. The first is got by deleting the last two columns and the last two rows. Modulo h1 is equal to y11. To get the determinant of the second principal minor, modulo h2, we delete the last column and the last row of equation 4.31. Modulo h2 is equal to parenthesis open y11, y12, y21, y22 parenthesis closed is equal to y11, y22 minus y21 in bracket squared. The modulo h is the third principal minor. Modulo h3 is equal to modulo h. Rules for minimum and maximum for multivariate function. If the value of modulo h1, modulo h2 and modulo h3 are greater than 0, then the Hessian is positive definite and hence satisfies condition for minimum. If absolute value h1 is less than 0, comma, absolute value h2 is greater than 0 and absolute value h3 is less than 0, then the Hessian are negative definite and hence satisfies condition for minimum. Bordered Hessian and unconstrained optimization. Let the utility function of a consumer be represented by this behavioral function. U is equal to minus 5x1 squared plus 10x1 plus x1x3 minus 2x2 squared plus 4x2 plus 2x2x3 minus 4x3 squared. Determine the level of consumption mix that maximizes the consumer's utility. The first order conditions are U1 is equal to minus 10x1 plus 10 plus x3 is equal to 0. U2 is equal to minus 4x2 plus 2x3 plus 4 is equal to 0. U3 is equal to x1 plus 2x2 minus 8x3 is equal to 0. Minus 10x1 plus x3 is equal to minus 10. Minus 4x2 plus 2x3 is equal to minus 4. x1 plus 2x2 minus 8x3 is equal to 0. This can be written in matrix form as in minus 10, 0, 1, 0, minus 4, 2, 1, 2, minus 8 in bracket. x1, x2, x3 in column in bracket is equal to minus 10, minus 4, 0 in bracket column. With the use of matrix inversion or Cramer's rule, we find out that x1 I stereo is equal to 1.04, x2 I stereo is equal to 1.22, and x3 I stereo is equal to 0.43. To be sure that this commodity bundle satisfy the maximization condition, we need to test for the second order condition. This can be done with the use of bordered Hessian. U11 is equal to minus 10, U12 is equal to 0, U13 is equal to 1, U21 is equal to 0, U22 is equal to minus 4, U23 is equal to 2, U31 is equal to 1, U32 is equal to 2, U33 is equal to minus 8. Absolute value of H is equal to minus 10, 0, 1, 0, minus 4, 2, 1, 2, minus 8 in bracket. Absolute value of H1 is equal to minus 10 less than 0. Absolute value of H2 is equal to 10, 0, 0, minus 4 in bracket is equal to minus 4 into bracket minus 10 minus 0 is equal to 40 greater than 0. Modulo H3 is equal to modulo H is equal to minus 10 into bracket 28 plus 4 is equal to minus 276 less than 0. Thus, the utility is maximized at the consumption level of x1 I stereo is equal to 1.04, x2 I stereo is equal to 1.22, and x3 I stereo is equal to 0.43. Bordered Hessian and constraint optimization. Let the production of a firm exhibit Cobb-Douglas of the form Q is equal to K raised to power 0.4, L raised to power 0.5. Let the cost per unit of capital K, that is PK, be 3, while the per unit cost of labor L, that is PL, be 4, and the total expenditure is 108. Determine the level of input combinations that gives maximum output. Maximum K raised to power 0.4, L raised to power 0.5. ST3PK plus 4PL is equal to 108. Set up the Lagrangian function. Z is equal to K raised to power 0.4, L raised to power 0.5 plus lambda into bracket 108 minus 3pk minus 4pl. Zk is equal to 0.4, K raised to power minus 0.6, L raised to power 0.5 minus 3 lambda is equal to 0. Zl is equal to 0.5, K raised to power 0.4, L raised to power minus 0.5 minus 4 lambda is equal to 0. Z lambda is equal to 108 minus 3pk minus 4pl is equal to 0. Solving for critical points, we have K is equal to 16, L is equal to 15. To test for the second order condition, we use border Hessian from the above information. ZKK is equal to minus 0.24 K raised to power minus 1.6 L raised to power 0.5. ZLL is equal to minus 0.25 K raised to power 0.4 L raised to power minus 1.5. ZLK is equal to ZKL is equal to 0.2 K raised to power minus 0.6 L raised to power minus 0.5. ZPK is equal to 3. ZPL is equal to 4. Hence, modulo H is equal to, bracket opened, minus 0.24 K raised to power minus 1.6 L raised to power 0.5. 0.2 K raised to power minus 0.6 L raised to power minus 0.5. 3. 0.2 K raised to power minus 0.6 L raised to power minus 0.5 minus 0.25 K raised to power 0.4 L raised to power minus 0.5. 4. 3, 4, 0. Modulo H1 is equal to 0.24 K raised to power minus 1.6 L raised to power 0.5 less than 0. Modulo H2 is equal to minus 0.24 K raised to power minus 1.6 L raised to power 0.5 in bracket minus 0.25 K raised to power 0.4 L raised to power minus 1.5 in bracket minus 0.2 K raised to power minus 0.6 L raised to power minus 0.5 in bracket 0.2 K raised to power minus 0.6 L raised to power minus 0.5 in bracket is equal to 0.06 K raised to power minus 0.2 L minus 0.04 K raised to power minus 1.2 is equal to 0.06 L over K raised to power 0.2 minus 0.04 over K raised to power 1.2 greater than 0. Solving for modulo H3, we find out that the value is actually less than 0. Thus, we have modulo H1 less than 0, H2 greater than 0, and H3 less than 0. We therefore can conclude that when the capital is hired up to 16 units and the labor is hired up to 15 units, maximum output will be realized. This is the end of study section 4. Thanks for listening.